when Nellie is hanging from a rope, and I think I'm just going to show the stick figure, otherwise what's his name, Lashkar, he will get traumatized, as he said last time. What we understand is that when somebody is hanging by the rope, then there is a force that is acting downward in this direction, that is the person's weight, mg, and there is tension on these two ropes, T1 and T2. Okay. Now let us just look exclusively at the forces alone. Okay, forget about the entire situation, just look at the forces alone. So there is a force mg acting in this direction, there is a force T1 acting in this direction, and there is another force T2 acting in this direction. Okay, now what we need to know is that, is the situation any situation of equilibrium? If is sigma f is equal to 0? You say yes, sigma f is equal to 0. Why? Because there is no movement over here. There is no change in the state of motion. Very good. So if there is no change in the state of motion, then this is true. How is it true? Add up the two tensions, T1 and T2. Okay. So this is the line parallel to T1, and this is the line parallel to T2. Of course, this is not a scale diagram. It's a rough diagram. So I won't get 100% accuracy, but I get lucky most of the time, and I get it more or less right. Now the resultant of these two vectors, okay, is this vector. Right? So this is your resultant vector T1 plus T2, or the resultant tension. Right? Now the resultant tension and the weight, these two would be equal and opposite to each other. And that is the reason why f is equal to 0. Because if you add these two up, these two are in a straight line, right? So there is no parallelogram possible. And since there is no parallelogram possible, if this force is acting in this direction, that is acting in the opposite direction, they are both equal, then their effects cancel each other out. Therefore, you can say TR's quantity, when we put a absolute value around it, I don't know if you know this from mathematics, but the absolute value of TR, that means the magnitude of TR, is equal to the magnitude of mg. So therefore, this situation arises.
Sir,
Yeah.
I got disconnected. I mean, my computer restarted, so I don't know what happened. Can you just summarize?
Yeah. Well, what is happening is I am recording this, so I will upload this later, so you can have a look immediately after that. But a quick summary is, we are looking at this situation, Nellie Newton hanging by a rope, not with her neck, but by her hand. Her weight is acting downwards. There is a tension in this direction, there's a tension in this direction. We only took out the forces over here because we are interested in the vector. We have T1, T2 and mg. You add T1 and T2 using the parallelogram rule, line parallel to T2, line parallel to T1. Add up those two by drawing the diagonal to those two. You get the resultant vector. The resultant vector is equal and opposite to mg. The absolute value, that means if you draw parallel lines around this variable, that means it's the absolute value. So the absolute value of TR is equal to the absolute value of mg. Of course, I'm saying absolute value because they are acting in opposite directions. Strictly speaking, one will be negative and one will be positive. That is why I put absolute value. because these two are the same in magnitude and they are acting in opposite directions, sigma f is equal to 0. So that is how we understand the situation.
Hmm.
So the question, of course, is asked now, what if the rope is not distributed in such a way that she's hanging right from the middle? So in this case, it looks like, and that was my intention, that she's hanging right from the middle. That means T1 will be equal to T2 in this situation. Okay, but it is of course possible that the point at which she holds the rope is not exactly the center. So this situation is also possible. Okay, so now what happens? How do we know what the tensions are in the two cases? So what we again know is that there is a force mg, the gravitational force acting downwards, and we know there is some tension on this rope T1 and some tension in this rope T2. But what we do not know is which rope has more tension. Actually, we know that you can easily see that T1 is greater than T2. The Burl-Gray situation tells us that that is what the case is going to be. But how do we understand this in terms of vectors? So again, let us erase this part and let us take out the forces over here. So mg is clear, it's acting in this direction. We know that the two forces are acting, one in that direction, and no, maybe it's a little more steeper than that, and one in this direction. I'm roughly doing this, again it's not to scale, so it may not be correct. Why am I just showing the directions, white dotted lines? That will be clear in a moment, because we do not know what is exactly T1 and T2. We have some idea that T1 is going to be greater than T2, but we don't know exactly by how much. Okay, so that is what we are trying to find out. Well, from the previous situation, what we know for sure is that since sigma f is equal to 0, right, there is a force resultant of these two vectors which is acting opposite to this. Yes? Is this argument clear?
Yeah.
I'm repeating it. Let us work
Yeah,
backward.
sir.
We know T1 and T2 exist, but we do not, and we know in what direction they are acting because the ropes are telling us that. But we do not, and we also know that T1 should be greater than T2, but we don't know exactly by how much. So how do we find out what is T1 and what is T2? Let us work backwards. We know sigma f is equal to 0 because of the situation. There is no change in the state of motion. So therefore, from the previous situation, we also know that T1 and T2, when you add them up, you get the resultant vector, which has to be equal in magnitude to mg and acting in the opposite direction. Is it clear so far?
Yes, sir.
Yeah.
Yeah, sir.
Yes, sir.
Right. Very good. If you are convinced about that, then my job is very easy. So now my question is, how much should this length be and how much should this length be so that the sum of those two makes this? In other words, it's like, when you cheat in mathematics a little bit by looking at the answer in the back of the book. You don't get a sum, you're struggling with it, then you say, okay, I'll just look at the back answer and then I will decide how to answer this problem. So it's a little bit like that. You got the resultant tension. Okay, the resultant tension. Why I know that? Because I know that the resultant tension has to be equal to mg in magnitude, and therefore it has to be acting in the opposite direction. Now my question is, what length over here and what length over here will make this? So how will you
So
answer that question? Yeah.
just draw some parallel lines which are intersecting the point T. I
Exactly.
mean,
So
Yeah.
find out the parallel lines, the line parallel to this which will intersect over there. Okay?
A line on that which
Yeah.
Basically, you have to draw the arrows where the intersection point is at the
Exactly.
resultant.
Yeah. So this line I take, okay, and I take it over there. Then I drop a perpendicular from there to this. Okay. And then I have to draw one parallel to this on this side. हाँ मिल गया. Okay, I hope you are able to see that. All right. So now, interestingly, what has happened is that I have got the two tensions exactly. So I have got one tension over here, that is my T1, and I have got another tension over here, that is T2. And it's absolutely clear from the parallelogram rule that T1 plus T2 will be equal to this TR. And a simple observation also tells you that T1's length is more than the length of T2. So therefore the tension on this rope is more than the tension on this rope. Okay, and if you do this on a graph sheet, then of course you also get the angle in between those two. So that is how you understand the Nellie-Newton situation.